My name is Betty Janad. I'm head up marketing over here at Solo, and we're very excited to have you join us. Before we get started here, this session is being recorded, and so we will then share that back out with you, as well as post it on our YouTube channel so that you can share with your colleagues. We will have a version of the slides available as well. So if you have a colleague that couldn't attend, don't worry, they'll get it, and we're happy to have you share this out. And with that, we will have the chat and the Q&A widgets are open. So please type in your questions as we go, as our speakers are presenting, and we'll handle them all at the end. And to kick this off, we've got Christian Posta, our global field CTO, and Scott Weiss, principal engineer, talking today about extending Envoy Proxy with WebAssembly. Christian, Scott?
Yeah, thanks all for joining. And I want to give a heads up that I am in the middle of, and hopefully coming down from, the flu. So my voice might be a little raspy, my head might be a little cloudy. But I did not want to miss this webinar. This is exciting stuff that's happening in the kind of application networking ecosystem. And Scott and I are here to kind of show you what's happening and explain why it's important, why it's exciting, and show you what we've been doing to enable this. So let's get started. So this is a solo.io webinar. We will be approximately following this agenda. We'll take a look at Envoy Proxy and some of the application networking components that can be used to build service mesh and various patterns with a service mesh. And then we'll look at how those same components can also be used to solve problems at the edge and at the boundaries of our architecture with ingress and API gateway and what the differences are between those two. And then we'll try to dig into what it means to extend these capabilities, some of the challenges of doing that, some of the reasons why you might want to do that, and then we'll get into where things are going in the community, especially focused on WebAssembly. So before we dive in, I just want to give you a quick level set of what we're doing here at Solo. We're heavily involved in these various communities that we'll be looking at, these open source communities that we'll be looking at today. But what we're doing at Solo is to try to help people along their journey of modernizing their application architectures. We know that they're adopting some of these new technologies, but we want to help people do it in such a way that they can be successful with these, because we know that as you start bringing in Kubernetes and Prometheus and Fluentd and Envoy and all of these pieces of technology, that can increase the complexity of your architectures. And what we want to do is help simplify that and help make it easier to adopt these technologies and be successful with them. So in the way we're looking at it is, as people start to go to a microservices style architecture where they have existing investments in their various technology vintages that are used to support the business, probably very successful, making a lot of money and so on, they're going to slowly and iteratively move to microservices. They need to start solving some of the challenges of, well, when you break things up into a bunch of different services, what is the entry point to those services? How do we define what that API looks like? And so for that, we've built an API gateway on top of Envoy Proxy, as an open source project called Glue. Now, as people get to microservices and start to scale out and have a bunch of different types of programming languages and frameworks deployed in their application architecture, they need to solve some of the challenges of service-to-service communication. There's going to be challenges around observing that communication, understanding it so that we can make decisions about when to change the traffic routing rules, when to enable or disable certain policies, when to reduce how to reduce the mean time to recovery and understand what's going on. So people are adopting service mesh to be able to do this. And what we're finding is service mesh is today pretty complicated to adopt and to operationalize. And it, especially when you get to non-trivial deployments across multiple clusters, that becomes difficult to unify the trust domains, unify the observability, panes of glass, to write rules that make sense, especially if you're doing multi-clusters across a on-premises deployment and a cloud deployment and so on. So what we're building is a way to manage that complexity, reduce the complexity, and make it so that people can actually adopt service mesh and be successful with it. And lastly, once we start to lay the foundation of being able to control, observe, and secure our network traffic, whether it's at the edge, whether it's between services, whether it's between boundaries, that enables a programmatic API that allows us to build the higher value tooling that we need to be able to deliver software faster and safely. So things like understanding the traffic patterns and controlling the routing, right? So we need to be able to adapt when traffic patterns change and effectively adapt the routing. So we need to build some control loop, something that's watching, something that's using these service mesh APIs to do that. Things like canary automation, things like chaos experimentation, things like debugging tools. These are all the higher value propositions of this sort of API-driven automation. And so for that, we've built a bunch of open source projects that assist with that, Autopilot being kind of a foundational operator framework for building on top of eService Mesh, as well as Loop, which is a record and replay debugging system on top of Autopilot, on top of a mesh, Glue Shot, which is a chaos experimentation tool, and so on. So we see this as a way to simplify the adoption of some of this technology, to enable you to be able to build powerful abstractions and automation on top of your network, things that we haven't been able to do in the past that bring a tremendous amount of value, especially when we go into deploying into cloud platforms. So that's what we're doing at Solo. Now, jumping right into the presentation, we're going to start to look at sort of the underpinnings of this architecture. We're going to look at a piece of technology, Envoy, that acts as what it is at its core is a proxy, right? But it is being used as a framework to enable the rest of this innovation or this ecosystem. So what is a proxy? If we start talking about that, a proxy is basically an intermediary through which traffic traverses or travels that provides a location where we can enable policy and enforce certain security parameters, where we can observe telemetry and siphon off metrics about what's happening in between the two endpoints that might be communicating. We could do things like load balancing and health checking and service discovery and so on. And we can do this independently from what the application code is written in, either on the client side or on the server side or provider side. So it doesn't matter. These things are talking over the network, and we're looking at the network in terms of L4 to L7, and this proxy can understand, especially when we start talking more deeply about Envoy, can understand request level and protocol specific requests or messages, and we can apply these policies and these rules regardless of how the applications were written. So when we start going down the path of, well, how do we solve service-to-service communication challenges? Services need to build for a dynamic and constantly changing infrastructure. So if we're talking about Kubernetes or other cloud platforms where the compute is ephemeral, it can be auto-scaled, we need to build our applications in such a way that we can react and adapt to those environments. And we need to solve for things like service discovery. We need to solve for things like timeouts and retries and circuit breaking, distributed tracing, telemetry observability, and so on. While in the past we did this in a very language and framework specific way, as I outlined in the previous slide, using proxies, we can offload some of that implementation detail into a proxy well suited to be able to handle the application networking concerns on behalf of the application. And in a service mesh architecture, once we start going down that path, we see that we deploy these proxies next to each application instance, which there we implement the networking capabilities. So any of those things that we were doing in the past, service discovery and routing and circuit breaking and so on, we can do that in the proxy outside of the application and apply these policies regardless of how we wrote the application. So you can think of these service proxies as a personal proxy or personal gateway into and out of the workloads. And working together, we can better reason about the system, its behavior, and so on, and we get consistent telemetry and security, like I said, regardless of how the service was written. Now, in a service mesh, that service proxy gives us a bunch of different control points, right? So at the granularity of the application instance, we can control what services are allowed to talk with which. We can control the transport and secure and encrypt the transport. We can give certain services routing rules to and from and around, maybe in some cases, failed services. So we need a point where we can define these rules and define these policies in a way that fits in with our existing, the organizations have a lot of assumptions built into the way that they run their processes, the way their workflows are organized, and so on. We need a way to influence those configurations at the service proxy level in a way that fits nicely within our organization. And we need to do that from a centralized location, centralized API, right? We don't want to log in to each one of these proxies for each instance of a service and try to configure it by loading, well, I don't know, say YAML files and hot restarting the service or the proxy and so on. So what we like is a centralized way of managing this configuration. And in a service mesh architecture, that's where the control plane comes into play. So the control plane is connecting up to the various service proxies under management and disseminating configuration and driving the policies into those proxies and how they behave. Now, like I was starting to explain, the control plane is kind of a decoupling point between the implementation details and the configuration details of a particular fleet of proxies and the way the organization has structured its, let's say, service registries, where it's pulling, maybe it already has existing systems for defining policies about services and how they're allowed to communicate with each other. So it's this decoupling point between how the organization actually works and the underlying data plane. Now, the same thing is true at the edge. So we're talking about services communicating with each other within a boundary, but we're also concerned about how traffic gets into that boundary. And at the edge, an API gateway may be useful to decouple what's happening within the boundary from what's happening or what the expectations are outside of that boundary. Now, Envoy, I've alluded to, is very well suited for the service proxy or service mesh pattern. And I also alluded to that Envoy is being used kind of as a framework or the underpinnings of this type of technology. As another example of Envoy's versatility in being able to solve these problems at the edge as well, with a little bit more focus, because the problems at the edge are not always exactly the same as those where we're solving east-west traffic. Right? The clients are unknown. The things outside the boundary, they have assumptions that we may not want to uphold within the boundary. For example, we might implement services in gRPC, or we might implement, so as an example, in enterprise of maybe newer protocols. As a realistic example of older protocols, we might have services implemented in SOAP or even older vintages of technology. And so what we expose outside the boundary, we might not want to expose those implementation details. We might want to have a nice, stable, maybe REST API. Maybe we want to use GraphQL, and we don't want to expose the implementation details of what's running within the boundary. We might have a very specific and customized security requirements, things that we want to support outside the boundary versus inside, and so forth. So the API gateway and the edge solve a different problem, but Envoy provides the kernel, you could say, or the core framework for being able to build that type of solution. So API gateway and a service mesh complement each other very well. They, in some cases, may use the same underlying technology, in this case, Envoy. And the examples that we're looking at here are Istio as an open source service mesh, and Glue as an open source API gateway, both built on Envoy, where Glue could be solving the edge and boundary concerns that we might have in terms of how we expose the rest of the cluster, and Istio or service mesh would solve the service-to-service communication. Now, as I said in the previous slides, the control plane, whether that is for a service mesh or whether that is for an API gateway, provides the ability to manage and control the data planes, but also provides a point of decoupling from the realities of the organization looking to adopt these technologies. And why that becomes interesting or important is that every organization has a slightly different way of working, different backend technologies, different workflows, processes, assumptions, and a one-size-fit-all solution will not work here. So because of that, we hope to have an extensible or customizable solution when we start to adopt these pieces of technology. Now, from the Envoy perspective, Envoy is the kernel or the core of these technologies, most of them, not all of them, but most of them. And Envoy was built from its foundation to be extensible. It was built from its foundation to be dynamically configured. So with these properties at the foundation of our technology, that should enable us to customize the behavior and fit things into the technology landscape that we already have and get the value out of these pieces of technology. So Envoy can be extended. You can see in this graphic here that we can add new filters in a filter chain. So there's a pipes and filters model, which may be familiar as not a new architecture. And we can plug in different filters or different modules to to change the behavior of the request processing in this pipeline. So for example, if we needed to add some new protocol support, right? So right now we have HTTP 1 and 2, we support gRPC, support things like Redis and Dynamo and MySQL and so on. Kafka just support just landed. And but if we needed to, like, we implement this in an organization that has maybe certain bespoke TCP based protocols or SOAP and so on, we can add these as filters to Envoy and extend the behavior of the data plane. Now, the way that works in Envoy today is that you need to build your extensions or your filters in the same language that Envoy is written in. And Envoy is written in C++, which is great. For a proxy like this, it's great that it's written in C++. It just makes it a little bit more, the bar's a little higher in terms of contributing customizations to it. And when you do, you have to statically compile this into the Envoy binary and then use that binary as your proxy, right? So you deviate from the upstream. Now, this is not like insurmountable. We do this at Solo, and we've built a lot of extensions to improve our ability to support the API gateway use case for example, Glue, but it's not ideal. It would be nice if we could enable folks to write these extensions in a language that they prefer and be able to still contribute that to Envoy. So as we start going forward, and in the not too distant future, this approach is taking shape and will be made available. And at Solo, we're working very closely with the community to significantly simplify what this looks like. And to do that, we are leveraging a technology called WebAssembly. Now, WebAssembly is a binary instruction format that was originally developed to be used in a JavaScript engine inside the browser. So how do we build a compact and very efficient running piece of code that would outperform what's being run in the browser for high compute type tasks? Now, it was written and developed from the position of being a compile target, right? So you can use C and C++, you could use something like Rust, you could use something in the not too distant future, things like Go or other garbage collected languages, to be able to compile down then into WebAssembly and then run that in a particular target. Now, it started off, originated in the browser, but we're seeing this applicability well outside the browser, and especially in proxy technologies like Envoy. Now, Envoy Proxy has begun, the community has begun introducing this WebAssembly or WASM support, and it should be upstream fairly soon. But I caution that it's not there yet, but it's very soon. It's coming. So what that looks like for extending Envoy is you write the filters and the codecs and the extensions that you want for your organization, or reuse existing code that you might already have, and compile that down into WebAssembly. Now, once you compile it down into WebAssembly, you can dynamically and safely and securely load that into Envoy at runtime. So what this means is you need a tool chain to be able to support this, to be able to support creating the new modules, compiling them down correctly against the specific APIs that Envoy might expect, and so on. And then a workflow to get them into Envoy itself and configure them. All right. So what this gives the community is, it opens the door to developers beyond C++. Right. You can use the base Envoy distribution without having to customize it, to differently from what's happening upstream. So you can just, whatever those differences are, you can combine them and assemble them at deployment time or at runtime, and still be on the base Envoy. It's a safe and secure way of bringing these modifications to Envoy. And Envoy, this can be supported in any of the technologies that leverage Envoy. But I will point out that it is not yet production ready. Like I said, it's still going to be merged upstream, but it is not too far off from being ready. So what we're doing at Solo is we're observing and excited about this potential from both a service mesh as well as an API gateway standpoint. But what we want to focus on, like we focus on with the rest of our products, is how do we simplify this experience? How do we make this approachable for everyone? What does it look like to, if you build the WebAssembly module, then what do you do with it? How do you catalog it? How do you track it? How do you audit it? How do you build the workflows around it to get it into production, into a running Envoy safely? And how do you share these extensions so more people can use them? And so on. So we've built a tool chain and a workflow to do this. And we're calling this the WebAssembly Hub. The WebAssembly Hub is where we can push these modules, evaluate them, audit them, and discover them, and pull them down and use them, and share them with others in our organization or publicly outside of our organization. So WebAssembly Hub and the accompanying CLI, WASME, facilitates this and simplifies this. So basically what we do is we can use WASME to bootstrap our new WebAssembly module in the language of our choice. We can then add the code that we need and then build it. And once we've built it, we can publish it to to the WebAssembly Hub, to a registry. And then from there, the rest of the community, we can just discover it and then pull it down and deploy it. Now, like I said, I'm super excited about this. This puts a lot of power back into the rightful hands of the people who are using this technology. And it enables them to more adequately fit the technology like service mesh and API gateways into their organization. And let's see if we can take a look at, so here's some of we can share these slides and you can take a look at this workflow, but let's jump into a demo. It's enough talking for now. Reach out to us on Twitter if there's questions. But Scott, Principal Software Engineer at Solo, been working quite a bit on this. Super excited to show this technology. Take it away.
Thanks, Christian. Give me a sec. Let me share my screen. Okay, cool. Hi, everybody. Thanks for the intro, Christian. So I'm going to show you today using the Glue API gateway with Envoy, and how we're using this new feature in WebAssembly to dynamically extend the proxy at runtime. So there's no need to rebuild, no need to redeploy. Everything is, you can customize your proxy without having to actually change your cluster. Let me show what that means. So this is all running on Kubernetes right now. All I have installed is Glue. If you're not familiar, Glue is an API gateway. It comes with a control plane components, and then we have this proxy here, which is Envoy. And we can actually see, if we want to, we can check out like the Envoy route table currently, what Glue is giving it. I won't get too deep into the weeds there, maybe if we have some time left over. But one of the things that I'll show is I'm going to, let's see, I'm going to create a route to this pet store application that I have deployed. just a basic JSON web service. This virtual service is the Glue equivalent of an ingress, if you're familiar with Kubernetes ingress, which is basically a way of defining some routes for external clients using a YAML. So I can apply this, and then I should be able to say to run curl, and you can see I can hit this /API pets through my. This is all running on GKE. If I echo that URL, you can try this at home if you want. Please don't DDoS my server. Okay, so we can see we have some. We just sent the request using curl that actually went through Envoy, and we can see that with this server Envoy header that we received. Yeah, so anyone who's not familiar with this, essentially this is output from this curl command, which sends requests. We see the request headers and then the response back that we got from Envoy, which went through Envoy to our pet store. So if I clear that, let me show you how we can actually extend the functionality now of that of Envoy. So one of the things Envoy is doing is manipulating headers. That's like a common use case. There are all sorts of different custom cases where we want to check a header, set something else. So I'll show you a basic demo of how we can do that with WebAssembly. So I'm going to use this CLI tool that we've built for ease of use called WASME. And I'm going to say WASME init test glue filter. Okay, I'm going to create a directory called test glue filter. I'm targeting the glue platform. We could do it interactively, right? Test glue filter. Choose my language as C++. We'll build it for glue, and we can cd into that directory, and we see it's created some files for us. Specifically, the one that we only care about is this filter.cc. The rest of it is boilerplate that we're going to use to build this in a second. And just to show you the content of that filter.cc, there's a lot of boilerplate in this, which we're working on boiling away. But essentially, this is in C++. As Christian mentioned, we have support for more languages coming. And WebAssembly itself, anything that compiles to WebAssembly will work. So it's just a matter of creating the bindings, which we've been working on with help from people in the Envoy community. So you'll see here, what we're going to do is we're going to actually add a header to the response that just says new header, and it's going to pull the value. So the key is new header, and the value is going to be something that the user can specify in configuration. So let's check that out. We're going to build this filter. Because that takes some time, I am going to show you another terminal where I already did it. This is what the end of that command looks like. And I built this filter here, this 1.3. So just to give a little context, the way that we have designed the hub, the WebAssembly Hub, is that these filters are stored as OCI images, just like Docker. So I can actually run wasme list, and I see these are all the filters that I've built with wasme on my local machine. I can run wasme push, and let's do that now, just like pushing a Docker image. So we're going to push that 1.5. It got pushed to the hub. We can see that it's there if we do wasme list published. This will show things that have been pushed rather than what's on your local. And we should see, I know it's a little cluttered, but we'll see that glue hello and the 1.35 got pushed. So just going back to our cluster.
Scott.
Yes.
Hey, Scott, just while you're, this is Christian. So while you're at this point right here and you just pushed, and as you start to go into the publish part, there was a question on the chat, and it said, why WASME Hub or WebAssembly Hub instead of a more generic repo like Artifactory and so on? So just keep that question in mind.
It's primarily, so our implementation is based off of an existing, so we use OCI images, which are the same way Docker images are stored, and there are other projects now starting to use OCI Helm. Helm charts can be stored as OCI images. You just need a compatible registry, essentially. So those Artifactory doesn't have, the only we basically had to build our own because none of the existing registries out there support like a more custom OCI image. They're kind of expecting Docker images right now, and there's one out there that supports Helm, but we've basically modified it. But you could use any compatible registry, as it's all client-side. It's just about using an image registry, and the logic there is that, I mean, there's actually a whole set of blogs that maybe we can link that discuss the benefits of using OCI images as like a cloud storage. But what it allows me to do by being able to push it with this tagged image to a cloud repo is that I can run a deploy and actually deploy my filter directly from the cloud to my cluster and see it live. So maybe we can just try that out. How does that sound? Christian?
Oh, sorry. Yeah. No, that was perfect. That's good.
Okay, cool. All right, so I'm gonna stop that build here. Oh no. Okay, I'm gonna open up a new. What I meant to say is I'm gonna open a new terminal window, and let me get WASME in my path. I'm gonna say my WASME list. Make sure my my image is there. Just verify that 1.3. Okay, now I want to try my curl again. Oh, whoops, URL, semi URL. Try my curl. I can see that I am not seeing that header. Okay, so let's see our filter in action. Let's actually deploy that thing. So all we have to do is write WASME deploy. Say it's for the target is glue, and WASME does support other targets. Depending on how you're running Envoy, there's a different way of configuring this, but WASME automates that for you. I specify my image, give it a unique ID, and then I can provide configuration for the filter itself. And I know that config because I happen to write it, but it's just arbitrary JSON. So we can deploy that, and we should see pretty quickly that now our header just got added. So I was able to actually add a filter dynamically to Envoy, to this pod that's running, without having to change any, redeploy anything, modify my Kubernetes deployments, zero downtime, everything done live on the wire, which is really nice. You know, it enables us to basically develop extensions for our proxy, you know, whether their applications are for security, monitoring, traffic control, and do that without having to manage the deployment lifecycle of the Envoy itself. You know, I can imagine filters being rolled out into test and staging before we roll that same filter right into production. So that's pretty neat. We have the WASME. So I can actually change this configuration pretty easily. So if I, it's another benefit that this automation gives us. So if I curl again, now you could, now you can see I've got, oh, there might be a bug in my filter. I take no responsibility. Looks like I added a header twice, but you can see that I'm updating the config dynamically. Oh, no, I think I know what it is. But I won't start debugging that now. WASME on deploy. And I think we have to do it twice, is my guess. I believe I added the on deploy. There we go. Okay, I had added the filter multiple times because you can use this to create multiple filters on Glue. And now our filters are removed and we're back to a vanilla Envoy. So yeah, I think that concludes this part of the demo.
Okay.
Thank you, everybody.
Thank you, Scott. Let me go back. I'm going to share my screen and I'll answer some of the questions that we had on.
Yeah, Christian, if you could put that slide up with all the links for people to check out the hub and.
Yeah, I'll end on that. So if you go to WebAssemblyHub.io, so Scott showed the workflow, bootstrapping, building, pushing to the hub. He explained why we used why we built the hub and that the back end of the hub is really just any OCI compliant registry. Now, there was a question on the chat. Let me pull that up. No, that wasn't there. It was. Now I don't see the. Oh, here we go. Okay, so there was a question about what type of extensions that you would find people would want to write for Envoy. Now, I mentioned a couple in the presentation, but if you go to WebAssemblyHub.io and click on Explore, you can see it's seeded with a few extensions already. We're in the process of building more, but this can give you a couple of ideas at least. So the three that we see here, actually all of them that we have here are available in Glue today as part of our API gateway, but they're built using the way of statically linking into the binary of Envoy, and so that makes up the proxy. But what we're doing is we're making those filters that we've written and statically compiled in LinkedIn into WebAssembly modules so that those can be reused at the API gateway or in any Envoy proxy. So for example, we have one that is able to do transformations. So we can do request level and response level, if I clicked on it, request level and response level transformations to a request as it comes in or leaves the proxy. We can do things like extend the list of metrics that Envoy keeps so that when Prometheus scrapes, we see these new metrics inside of Envoy. One of the functionalities of our API gateway that we're converting to a WebAssembly is the ability to call AWS Lambda. And so what this does under the covers is compute the correct signatures to be able to make the request directly to Lambda, so not through API gateway or any of that. It goes directly from Glue to the Lambda and invokes the Lambda and so on. So we've built functionality to be able to do web application firewalling, to be able to screen responses that are going back and eliminate or mask certain pieces of data like credit card numbers or social security numbers and so on. Be able to do translations between very specific protocols and so forth. So this is there's a set of examples. The actual examples are limitless, as we find when we work with our customers and partners to adopt either gateways or service mesh. We run into this quite frequently.
Mind if I just add a little bit to that?
Yeah, go ahead, Scott.
Yeah, so one of the things that we've seen, we actually have already had a contributor for even though we're still kind of building out the infrastructure for the WebAssembly Hub, we've had our first contribution for a user who's building a filter in Rust. And basically there's a lot of users who have a custom use case, which is maybe possible using the Envoy filters in a complex arrangement, but there's something very specific. They want a behavior where, based on the presence of one header, they want to modify or change another header. It's a common use case, but everyone has their own sort of version of it. And by WebAssembly allows people to just build their own extensions in the language they're comfortable with without needing to become experts in Envoy and learn how it might be possible using some configuration of the lower level tooling.
Awesome. Yeah, so go to WebAssemblyHub.io, check that out. We see here, I'm gonna put the links up so that you all can see that. And then I'm gonna get to the next question, which is, what limitations are there with the WASM Envoy filter? For example, if I have C++ filter today, I want to change the WASM filters to promise that all symbols used in C++ will have analogous interfaces in the WASM interface. Mm-hmm. And the answer is, so first of all, this is still evolving. And so as of right now, the answer is no, but it is still evolving. I can link to the file that basically contains all the functions that are available in WASM, the WASM filter. So let me just put that in the chat. That was for Dan, who asked that question. I can
Yeah, I
link
can
to
also
that.
add a little bit to that.
Oh, go for it, Scott.
Yeah.
There's a
So
question.
there's a subset of the full Envoy API that's available right now to WASM filters, and they're going to be exposing everything. So it'll be that'll work. Also,